So this is a quick software demo of the Centeo Control Center, the C3 software. So the first thing to do is just open the software up. Okay, so the first thing you get when you start the software is a quick splash screen that shows you kind of the status. At the moment there's an experiment running, so I'm just going to actually stop that. And I'll just delete that. Okay, so when you first come to the unit, you often have a kind of fairly fresh screen like this. And the first thing we're going to do is, I'm just going to quickly set up an experiment just to get things going. So it's File, New, Experiment Name, Test. I'll go through this in more detail in a second run through in a minute, but let me just fill in some numbers. So relative humidity, I'll put in 50 for today. 20 degrees C. I'm going to run this unit from 4 to 20 degrees C. Next. I'm not going to label up the individual wells, but I could do. And that's it. The experiment started. So I just wanted to do a quick start, and then I'll go through in some detail how to actually do that. So as I say, when you first start up the software, you'll get a screen that looks like this. I know that at the moment the unit's running because I can see an experimental plan where it says that's running, and I can see the plate status which also says it's running. So these two things are in sync with one another. So when you want to write an experiment, just go File, New, give it an experimental name, so I'll call it Test 2. Experimental description, just a demo. It's asking us the temperature logging interval. By default that's 20, so that means that this will save every minute. The quick calculation is just 3 times 20 equals 60 seconds, i.e. every minute. If we decrease that to 2, then we'll be saving every 6 seconds. If we increase this number to something like 60, then we'll be saving every 3 minutes. So I'll keep it at 20. The temperature error threshold is just asking what's the kind of precision with which you want to control temperature. Is controlling temperature plus or minus 1 degree C okay, or do you want to do better than that? I'm running a TG40, so I don't need to play with this, but there are other units out there. There's the TG40, the TR18, the TR40, but I have a TG40. So I have my name, I have my description, I have my save rate, I have my precision, I know I've got the right unit, so I'll just go next. Right, now it does ask you first of all 2 questions. The average relative humidity. The question is, what's the humidity in the lab that you're working in? And if you're not sure, then one way of finding out is to kind of go to Google. So I'll quickly bring up this Google window, and I'll just go weather. Oops. I'll do weather in London today. So today the weather in London is 22 degrees C with a humidity of 57. If you have a thermometer and a humidity sensor in the office, even better, or in your lab, even better, but otherwise, just use Google. So the average humidity is 57%. The highest ambient temperature is 22 degrees. Now I have 3 modes of operation. I can either operate exclusively above ambient temperature, or I can set all channels to the same temperature, or I can actually have each channel at individual temperatures. So for example 12, 16, 20, 24, 28. Now these 2 numbers are important, this average relative humidity and highest temperature. the message here is if you're working in a well air-conditioned lab, then you can get the most from the unit. So for example, if in an air-conditioned room, you might expect a humidity of something like 40%. If the temperature in that room was 18 or maybe even 20, that really influences the minimum temperatures that you can achieve. So effectively, the smaller this number and the smaller this number, then the greater range of operation this device has. And this is due to the dew point in the atmosphere. You can't have a very cold block sitting in a fairly damp environment, because it is going to cause precipitation. So that's why the software asks these two questions. Now if you're only going to use the unit kind of briefly, it doesn't really matter, but as you know, crystallization experiments can take several weeks. So after that time, if you really are working in a kind of warm, humid environment, you are going to get precipitation. So it is good to operate within a fairly dry air-conditioned lab. So here I'll set it to 4, 8, 12, 16 and 20. And what we do is go next, and then we can start putting in what's actually in those wells. And I'll just do a few of them just to kind of save time. And that's it. I've written myself a second plan. Now this second plan is actually not running at the moment, it's still running the first plan. And so what I've done is I've just highlighted the first plan. I'm just going to go along the tabs now just so we can see how that works. So we have a summary. At the moment, this unit, I've told it to go to these 4 temperatures: 4, 8, 12, 16 and 20. Row 5 has got to just very close to 20. Row 4 has got very close to 16. Row 3 is on its way down. Row 2 is on its way down, and so is row 1. So it takes generally about less than 10 minutes for all 5 rows to reach the set point. But that's what it's doing. And now in real time, it's also graphing the data as well, so you can kind of see what the temperature profiles are doing. And if we just look at row 5, it had us a set point of 20, and you can see that it brought it down from about 24 down to 20, so that's just perfect. That's row 5, and row 4 is similar. It was a little bit cooler, row 4 was, but now you can see it's brought it down to about 16. So we have a nice summary section. You can see now that row 3 is almost at its set point. We have a graph section where we can see the temperature. And there's another useful tab called ramps. And this is if you want to apply temperature oscillations or you want to provide temperature profiles. And there are a few boxes to fill in when applying ramps. The useful thing about ramps is you don't have to know ahead of time what it is you're going to do. If you just run static temperature experiments and those cause your protein to crystallize, great. But if you find that's not working, you might want to start increasing or decreasing temperature depending on if you have normal or retrograde solubility of your proteins. So let's say we're going to increase the temperature by about 2 degrees, and this will apply it to actually all the rows, and it's going to take place, that 2 degrees rise is going to take place over about 2 hours. And when am I going to start that experiment? So I'm doing this video today. It's the 10th of July 2013 at 3 o'clock. I want this to happen at 4 o'clock. And that's it. It's quickly saved a ramp there, and it will basically go to a new set point, which is 2 degrees higher than the current set point, and just stay there. So if you so wish, you could do another temperature ramp. Let's say I wanted to do another temperature ramp this evening, around about 9 o'clock, and I'll just hit save there, and then that puts in another temperature ramp. So you'll have a temperature profile, static temperature, it'll rise by 2 degrees over 2 hours. It'll then hold it until the next time point comes up and then rise it by 2 degrees C. So it's easy to apply ramps, and you don't have to have thought of the ramps ahead of time in order to apply them. Okay, great. And now that experiment actually isn't running because it's obviously this experiment that's running, but I just wanted to show you how easy it is to do ramps. So in summary, that's what we have. The unit at the moment, you can see just in the time that I've done this video, first row 5 rather is almost at its set point, row 4 is at its set point, row 3, row 2, and then row 1's just on its way down to 4 degrees C here, so you can see that's running. And that's really it. Software is very simple, intuitive, and a pleasure to use. If you have any questions, please contact us at www.centeo.com. Thank you very much.